What is chance of classification of a signal? That is, how can we classify a signal, or what are the basic types of a signal? So if you remember, we have seen that a signal or any signal can be represented in a two-dimensional space. One is where this represents the x-axis and this represents the y-axis. Now let's suppose if x, or if we replace x by that of t, we suppose that the x-axis or the independent variable in this particular case is time, and the function that represents a signal is x of t, and it is placed along the dependent variable or along the y-axis. Now based on this particular nomenclature, any signal can be classified into different types. That is, a signal can be classified with respect to time, as well as a signal can be classified with respect to the values of the function. Now if we want to classify a signal with respect to time, or if we want to look at the behavior of the signal along the time axis, then it can be classified into two types. One is the continuous time signal, and second is the discrete time signal. Now if you look at their names, so it is also mentioning time in both cases, continuous time and discrete time. So in this particular case, we are interested what is the behavior of the signal along the time axis or along the independent axis. Now, a continuous time signal is that type of a signal in which the independent variable changes continuously with respect to time. Now, if we consider a signal that looks something like this, okay, and if t is along the x-axis, so in this particular case, the value of the signal, if you can see, it is changing continuously with respect to time. However, to define a continuous time signal more accurately, we can say that a continuous time signal is that type of a signal which is defined at each and every interval of the time. Or in other words, a continuous time signal is that type of a signal in which the dependent variable t is defined for each and every value. The independent variable t is defined for each and every value of the dependent variable x of t, and vice versa. What do you mean by this particular definition? Let's suppose if we consider this particular point, okay, let's suppose if we consider this particular point, so we can see then a signal or a particular value of a signal is present at this time interval. Now if we consider another time interval, let's suppose this is t is equal to 0 and this is t is equal to 1. So we can also observe that a signal is defined for this particular instant of time as well. Now if we consider a time between 0 and 1, so we can also see that a signal is defined for this particular interval as well. No matter whichever time, no matter whichever location of time we select along the x-axis, at that particular instant a signal will exist and a signal will have a particular amount of value. So this type of a signal which is defined for each and every interval of the time is commonly referred to as the continuous time signal. Now another definition that we commonly give for continuous time signal is it has infinite number of points between any two intervals. That is, let's suppose if a signal is continuous a long time, so one feature of continuity commonly be expressed as there are infinite number of points between any two intervals. Let's suppose if we consider interval between, let's suppose if we consider an interval between 0 and 1. Okay, so what will be the center of this particular point? If it is a continuous time, so the center of 0 and 1 will be 0.5. Now, Let's suppose what will be the center of 0.5 and 0, that is 0.25. In simple words, there will be infinite number of values between 0 and 1 since it is continuous in nature. And for each and every value of the time, there will be a value of the signal along the y-axis. So in simple words, a continuous time signal is that type of a signal which is defined for each and every interval of the given time. For example, let us consider a simple example of a wave or a signal in which you can see that a signal is defined for each and every interval of time. If we look at time is equal to 0, so we have a particular value of the signal. If we look at time is equal to 1, so we have a particular value of a signal. If we look at time is equal to 2, similarly, if we look at time is equal to 1.5, so we have a particular value of a signal. Now somewhere between 1 and 1.5, so whichever time we select, there will be a value of a signal present along the y-axis. So such type of a signal which is defined at each and every interval of time is commonly referred to as a continuous time signal. Similarly, if you look at this particular signal and if you look the continuity of a signal along the time, so it can be observed that this signal is defined for each and every interval of time. If you look at 0, if you look at 0.5, if you look at 0.25, 0.75, whichever value you take along the time axis, so a signal will have a particular value at that instant of time. So such type of a signal which is defined for each and every interval of time is commonly referred to as a continuous time signal. Now, for example, if we consider a signal that looks something like this. Now, in this particular case, if you look at this particular point, so as there is no signal at this time interval. Similarly, if you look at this particular point, so no value of the signal exists at this particular point. So such a signal cannot be called as a continuous time signal. This is a signal that lies under the definition of a discrete time signal. So we'll be discussing discrete time signals in the next topic. Now, what is a discrete time signal? So a discrete time signal, unlike continuous time signal, a discrete time signal are represented for a given number of defined values that are pure integer and no fraction over a period of time n. That is, let me explain it more accurately with the help of a figure. So if you look at this particular figure, so this is a typical example of a discrete time signal. Now, discrete time signal is actually that type of a signal in which there is no continuity along the time axis. In other words, the signal is defined only at specific intervals of time, and those intervals of time are usually pure integer values. They are non-fractional values. So such a signal which is commonly defined at specific intervals of time is commonly referred to as a discrete time signal. Similarly, if you look at this particular signal, so the signal is starting at n is equal to 0. Similarly, there is no signal present in between this particular point. Similarly, again the signal is starting at n is equal to 1, then a signal is starting at n is equal to 2, and so on. So these are the typical examples of the discrete time signal in which there exists no continuity along the time axis, and the signal or the values of the signal are defined only at discrete or specific or non-fractional values. They are defined only at specific integer values across the time axis. So the definition, the intensity levels of the signal or the values of the signal are defined at discrete intervals of time. That is, discrete means discontinuous. Okay, if you look at this particular point, so a signal is defined at 0, then there is a discontinuity in the value of the signal. Then again the signal is defined at n is equal to 1, then there is discontinuity in the signal. Okay, so that's why it's called a discrete time signal, because in a discrete time signal, the signal will be defined only at discrete intervals. And discrete intervals are those intervals which are not continuous in nature.